Look at this space. Every linear transformation is a mathematical instruction that stretches and skews the grid of our coordinate system. To understand these transformations, we rely on eigendecomposition. By factoring a matrix into the form A equals PDP inverse, we decouple the distortion into simple, independent scalar stretches along invariant axes. We call these eigenvectors. This elegant decoupling carries a strict mathematical constraint. It requires a perfectly square matrix. Even some square matrices fail this test. If a matrix lacks enough independent eigenvectors to form a complete basis for the space, it is a defective matrix. The formula breaks down. This pure math requirement collides with reality. Whether you are processing high-resolution images, user behavior logs, or machine learning training sets, real-world data is almost always rectangular. Relying solely on eigendecomposition for applied mathematics is a pedagogical fallacy. To compute the geometry of actual data, we need a factorization method that never breaks. That method is the singular value decomposition, or SVD. Unlike eigendecomposition, SVD is guaranteed to exist for literally any matrix, regardless of its shape or symmetry. This mathematical guarantee supports most modern computational systems. Quantum state calculations, computer vision algorithms, and massive recommendation engines all rely on this stability. SVD decodes the geometric structure of high-dimensional information, providing the stable coordinate system necessary for data that the standard eigenvector approach cannot resolve. To build a universal factorization, we must start with an absolute guarantee. In linear algebra, that bedrock is the spectral theorem. The theorem carries a strict requirement. It only applies to real symmetric matrices, where the matrix is exactly equal to its own transpose. If that condition is met, the theorem provides two powerful mathematical guarantees. First, all eigenvalues produced will be real numbers, avoiding complex imaginary outputs. The second, more crucial guarantee is that the matrix will always possess a perfectly orthogonal basis of eigenvectors. As the circle stretches into an ellipse, the transformation occurs along axes that remain strictly perpendicular to one another. Symmetry dictates a perfectly decoupled, right-angled coordinate system. This is the exact geometric foundation required to process messy, real-world data. This leaves us with a structural problem. How do we apply a theorem that demands perfect symmetry to an arbitrary rectangular dataset of size m by n? We force it. Multiplying a rectangular matrix A by A transpose mathematically forges perfect symmetry. This first operation, A transpose A, analyzes variance between columns. Reversing it to A times A transpose creates another perfect square matrix, mapping relationships between rows. By mathematical law, both resulting squares are strictly symmetric and positive semi-definite. Because we have constructed these symmetric matrices, the spectral theorem now applies to them. We have unlocked a guarantee of perfectly perpendicular axes. A simple multiplication by A transpose allows us to bypass the geometric limits of raw rectangular data, extracting perfect orthogonal geometry from any arbitrary dataset. This leads directly to the singular value decomposition. An arbitrary matrix A splits into three distinct components: U, sigma, and V transpose. The blue V transpose matrix contains right singular vectors, orthogonal eigenvectors from A transpose A. They represent an initial rotation that aligns the input space. The red U matrix holds our left singular vectors. These are the orthogonal eigenvectors derived from the A times A transpose operation. The yellow sigma matrix contains the singular values. Geometrically, it stretches the newly aligned axes without skewing, morphing the grid into an ellipsoid. Finally, the red U matrix applies one last rotation, aligning the space into its ultimate target dimensions. Every linear map breaks down into this precise sequence: an initial rotation, a pure scale along orthogonal axes, and a final rotation. Now we can compress this data. The Eckart-Young theorem is the mathematical rule governing how to optimally shrink the information inside the sigma matrix. Look at this distribution. By discarding the smallest singular values in sigma and keeping only the top k values, we generate the mathematical best fit approximation of the entire original matrix. As the third axis squalls down to 0, the core shape remains intact. The singular values we throw away represent the lowest directions of variance. We systematically eliminate mathematical noise while preserving the dominant signal. The Eckart-Young theorem proves that SVD is a prescriptive tool. It calculates the geometry of a dataset and identifies exactly which dimensions actually matter. This mechanism is known in data science as principal component analysis, or PCA. It is the direct application of SVD on a mean-centered dataset to locate the orthogonal directions of maximum variance. In this context, our right singular vectors become the principal component directions. The singular values dictate the exact percentage of total variance captured along each axis. We can translate these abstract vectors directly into modern programming architecture. A single line of code in Python's NumPy extracts the U, sigma, and V transpose matrices, instantly computing the principal components of massive point cloud datasets. SVD moves linear algebra out of the classroom and into production, providing the mathematical framework to process the massive rectangular datasets defining modern data science.